Good morning, everyone, and welcome to the IBM Qiskit Quantum Seminar series dedicated to you, the research and academic quantum communities. It is my pleasure to welcome you here today, Friday at noon Eastern Time, which is our favorite recurrent time for 164 Fridays in a row, skipping one or two for the holiday that's occasionally biased. So today, in just a minute, I'll be thrilled to roll out for you this week's episode with Professor Igor Lesenovsky from the University of Tübingen, Germany. Before we get there, I'm very glad you joined us on time because we have a tradition to type in the chat. Where are you tuning in from? I see Paul here has also added a little box right below that reminds us of our favorite question at the start of this episode. We always love to see where everyone is from and to warm up the fingers for questions, discussions, and keeping this seminar interactive. Because you can always go back and rewatch the recording, but you can only have discussions with the speaker, myself, and the rest of the folks here, Fridays at noon Eastern. So to know what's coming up, click like and subscribe. Without much further ado, folks, and by the way, as comments are streaming in, I see we have people from New York, Oregon, Toronto, Vancouver, Madrid, Delhi, India. Thank you very much, Deepak, for the congratulations on our latest paper on Fibonacci anyons. Big Island, Hawaii. Nick, we are all wishing to be there with you. And yes, I see some of you are commenting on the background. I'm in our small satellite New York IBM office next to Grand Central. So that is the Empire. There it is. Where is? There we go. That's the Empire State Building behind me. So that's where I am today. So folks, with that, it's time to get started. Welcome to episode 164. I'm your host, Zlatko Minev from IBM Quantum, and it is my pleasure to welcome Professor Igor Lesenovsky from the University of Tübingen, Germany. Hello, Igor. How are you today?
I'm fine. I'm great. Enjoy being here. Good afternoon from Tübingen, Germany.
Yes, we had a lot of fun pronouncing Tübingen at the beginning here. And thank you for answering our favorite question. Before I turn the stage over to you, allow me to introduce you to folks. Igor earned his PhD from the University of Heidelberg, Germany in 2006, focusing on the atomic physics of Rydberg atoms. Igor then moved to a postdoc at the Institute of Electronic Structure and Laser on the island of Crete in Greece, selecting a wonderful location, and subsequently to the University of Innsbruck, Austria. In 2009, Igor started his group at the University of Nottingham, and since 2019, Igor has been at the University of Tübingen, Germany, which, by the way, I learned from Igor, was founded in the 15th century, one of the oldest universities in Europe. So please welcome Igor.
Thanks a lot for the kind introduction. So what I'm going to talk today about is so-called thermodynamics of quantum trajectories and how to realize it and exploit it on a quantum computer. Before jumping into the science, just building onto what it was said before, I just want to show you where Tübingen is. It's located in the southwest of Germany. It's a very picturesque town, medieval town center. So please go there when you are in Germany, when you have the chance. It's near Stuttgart. It's just a 45 minutes trip from there. So what I'm going to talk about today was mainly pushed by Federico Carollo, who's a postdoc in my group, who's moving to a permanent position as an associate professor in Coventry, and by a PhD student, Marcel Zech. And also parts of these ideas, and later on I will also connect to this in more detail, are due to my time at the University of Nottingham, where I met my dear friend Juan Garahan, who actually is an expert in soft matter physics. And what we have been trying since then is to marry concepts from soft matter physics with interesting quantum dynamical aspects. And this is what this talk is going to be about. So just to give you an idea of what to expect, so we start with a brief motivation why we are doing this. I will then tell you some basics, give you a crash course on this idea behind thermodynamics of quantum jump trajectories. It's related to large deviation functions and the introduction of thermodynamic potentials, which you might be familiar with, but from a slightly different perspective. And I'll show you that you can make it in a nice connection also to counting statistics of open systems. And third part will be related on how to do this on a quantum computer. And then the fourth part, hope we are getting there, is so to say, another motivation why one actually would want to do this on a quantum computer, because it will hopefully, this is at least the idea that I want to sell here, allow us to study interesting dynamical phenomena, dynamical phase transitions in open systems, which also relate to physics that people typically study in the context of soft matter physics, when, for instance, looking at the problem of glasses and how to describe those substances. All right, so what does this whole presentation build on? So we are dealing with open quantum systems, and typically the sketch that one does is the one that I show here to the top right. So you have a quantum system that is embedded in an external environment, and this interplay between dynamics within the quantum system and the coupling to the environment can be actually exploited for the creation of correlated quantum states, or you can also use this as a means to run essentially computation. Yeah? And the basic idea, I don't want to dwell on this too much, is that you have an initial state, you run your open system dynamics, and then you arrive in an interesting state. And as so to say, sketched here, this might even be a pure state, although the whole dynamics undergone by this open quantum system is inherently dissipative. So what we are interested in for the purpose of this talk is to look at the output. So because due to the coupling between this quantum system of interest and the environment, we have, for instance, an exchange of quanta. Yeah? So simplest setting is an atom sitting in the radiation field. We drive the atom. This atom emits photons, and I can make a record of these photon emissions over time. So these types of plots will appear throughout the talk, where we have here the time axis, and then we have here those strokes. They are red here, later they will become blue. So those are just the events at the times at which we, for instance, record the emission of a photon in the experiment. And what we want to do is we want to ask, how can we classify this output? Yeah, we can do this via full counting statistics, which then leads us to real events and gives information on the system. We can also then ask, building on this information, can we use somehow this output to do metrology? Yeah, for instance, measure parameters of this quantum system. And we can ask quite generally, what do we have to do in order to control this output to turn maybe boring output into something interesting? So just to set the stage, there will be there will be many formulas, but okay, I'm trying to be gentle and pedagogical in introducing those. And when I talk about open systems, we, for the purpose of this talk, take, so to say, the simplest theoretical manifestation of open system dynamics, where the evolution of a system is governed by a so-called Lindblad master equation. This is this beast that is plotted here. So on the left, you have the time derivative of the state vector of the system, so the density matrix. And essentially, there are two effects that determine the evolution of this state. So one is this part here, which depends on the so-called quantum Hamiltonian H. Yeah, so it's the commutator term that effectuates the coherent dynamics. And then on top of these coherent evolution, you also can have incoherent processes. For instance, processes which give rise to irreversible photon emission. And what we want to do, and we will do this in great detail in what follows, is to go from this deterministic equation to the trajectories by performing what's going under the name unraveling quite in general. So we want to unravel this equation in, so to say, stochastic realizations, which then gives rise to photon emission signals, for instance, that you can monitor on the experiment. So now let's ask what stuff one can actually do. Yeah, so I mean, this is still part of the motivation and question that we have been working on already some time ago, that shows you perhaps in a nutshell, okay, what is possible, and what we are aiming at is the following. So consider an open system. So here it's just, for the sake of simplicity, a very simple one, 3 spins. So the evolution is governed by a Hamiltonian, and these L operator, jump operators that are responsible for the dissipation. And now what you can do is you can now observe what the system is emitting actually into the bath. And for the sake of simplicity, imagine this really as atoms that are interacting and then emitting photon into the environment. And we assume that we can detect all these photons perfectly well. As a theorist, you are allowed to assume that. So then you create, and I showed you this before, a record here of this photon emission signal. So this is just one particular realization. So you see, I let time run, and then at certain points in time, I detect a click. Yeah, and the number of photons that I detect in this trajectory is here just Ka, for instance. But now I can also ask in general, so what is the probability to detect K photons in such a trajectory of length t? So this is an object that we can actually calculate. I will show you in a minute how this is done. And this gives you a probability distribution. This is, so to say, the object that encodes the so-called counting statistics. And then you see, well, certainly there is some peak, which here in this distribution, which is associated with typical statistics. I mean, this is the typical trajectory, and the number of photons in it is close to this Ka. But then there are also rare events which lie in the tail of this distribution, and because they lie in the tail of this distribution, they're also exponentially suppressed and unlikely. But well, it could be that those are actually interesting trajectories. And now the question is it possible, to modify the system, so to go from the original Hamiltonian and dissipative processes to some new so-called biased Hamiltonian or biased dissipative processes, to turn these rare trajectories here that appear in the tails of the distribution to become the common trajectory, and basically at the level of the counting statistics that will entail a shift of this distribution so that it's now peaked around the value of K, which before corresponded to the rare events. So this is, so to say, what we want to do. We bias the dynamics of an open system so that formerly rare events can become typical. Okay, so how can one do this? So this is the first question. So what's the general framework here? This is what I'm going to answer within the next slide, and there will be also a very neat connection to thermodynamics. And then later on, we will try to understand how this can be done in practice, because there are some subtleties to this procedure, because this dynamics or this kind of biasing at first glance seems unphysical, but it turns out that one can actually turn this into some physical dynamics that ultimately can also be implemented on a quantum computer, as I will show you. All right, so as I said, we are looking at open quantum systems governed by the master equation, and so I showed you now two-level atoms already a few times. Just to be concrete, when we have a two-level atom on resonance, so the rate with which you go between the ground state and the excited state is given by this parameter omega, which is called the Rabi frequency. And then you have also here this so-called jump operator L, which let's say demotes an excited atom to a ground state atom, and this happens randomly with a rate that is given by this kappa. So now suppose you have such a system in your lab, and this is definitely possible to do. Now you want to record the photon emission signal, and this gives rise to such a trajectory, quantum jump trajectory, use your favorite name. And now the idea, that, so to say, underlies this thermodynamic framework that we want to develop in order to classify these trajectories is the following. So, and I think it's best explained by mapping these trajectories to something probably most of us are familiar with, namely the physics of an Ising model in thermodynamic equilibrium. And the idea is here that you basically regard now time as some fictitious space, and you say now, well, in this one-dimensional space, I place my spins, and every time there is a no emission, I, so to say, by defining a discrete time bin, when there are no emissions, I say I have a downspin, and if there are emissions, I have an upspin. And you see, Okay, it's not a one-to-one mapping here, but you see the idea, every emission event in this kind of mapping can be identified with an upspin, while the absence of emission result in the time when dt amounts to a downspin. So like this, you can establish a correspondence between such a trajectory of the photon count and a microstate of one-dimensional ensemble of spins. So, and what we want to do now is to, as I said, develop a thermodynamic formalism that does not deal with the microscopics. So I'm not really interested in these microscopic manifestations, but I want to understand what are the macroscopic properties of the system. So for instance, I'm interested in so-called order parameters, which in the case of spin systems would be certainly the magnetization. But in the context of such a trajectory here, this could be the emission rate, the typical emission rate, the number of photons emitted per time unit. Okay, so how can we access this quantity? So starting point is again the master equation, and here it's a little bit simplified because we just say we have, so to say, one channel through which our system of interest emits a photon, like this two-level system that I showed you before, where I have only this one jump operator L. And now you see, if you look at the master equation, that there are terms that, so to say, can be interpreted, and this is the quantum jump term, as a term that relates the state of the system before a photon emission to the state of the system after a photon emission. So this is this term. So this is the so-called quantum jump term. And if you think of rho as the state before a photon emission, then after the photon emission, you will be in the state L rho L dagger. So you, in quotes, perform some kind of projection. And this you can formalize. You can introduce the state rho k, which is the quantum state of the system conditioned on the observation of k photons, k quantum jumps. And then you see very nicely, once you write the equation of motion for this conditioned state, that indeed what I just tried to convey becomes manifest at the level of this equation, namely that this quantum jump term here feeds information on the state which I had when I observed k minus 1 photons into the evolution of the state that is conditioned on the observation of k photons. So this is now turning the master equation, the original one that only, so to say, considers the system degree of freedom, into a whole hierarchy of coupled differential equations. This sounds bad at first glance because the problem seems to have become more complicated. But the neat thing is now that I have performed this unraveling that I was mentioning before, and I can keep track of the number of photons that are emitted in the course of the system evolution. So I gain information on the trajectories. And now I can just ask, well, what is actually the probability to have observed after some time t, k photons? And in fact, this is simply given by the trace of this conditioned state here. So solving this equation, you can calculate this, and you can calculate also this histogram.
So Igor, maybe a couple quick clarification questions
Sure.
here. So the top line here is the standard master equation
Indeed.
Of an unraveled system. Then the next line, you're saying I should think of this as many equations, not just one.
Indeed, because you index, so to say, the conditioned state by the number of photons that have been emitted by the system.
Okay. So that's I should not confuse this equation with the with like an unraveling equation of a particular trajectory instance, right?
Let's say I'm using the notion unraveling in a loose sense here. Yeah. So what I wanted to convey is that at least we get now information on what the system outputs. So I can now make statements, yeah, on. There's no stochastic unraveling whatsoever. Yeah. So I understand your question, and of course, it's an important clarification. But at least now at this level, I see, so to say, something about the photon emission. I know, so to say, how many photons have been emitted from the system by a certain time t.
Right. Okay. So maybe to rephrase it, yeah, this is not a stochastic unraveling. This is actually a
Correct.
deterministic equation of coupled systems.
Absolutely.
There's just many of them. So this is not like Ito Stratinovich. We don't need to worry about any of this. This is, but you've rewritten it in a way where you can kind of account for each branch set.
No, it's exactly this. Yeah. So I mean, you can decide at every time step whether you emit a photon or not, and whether you go one way or the other. Yeah, and you have still all branches somehow here simultaneously running. Whereas if you were doing this,
here maybe that's also.
Say again, please.
The branches are not interfering with each other, I guess.
No, because I mean they are clearly, so to say, separable. I mean, once you have emitted a photon, there's no interference, so to say, with another state where you have a different number of photons emitted. So they are all living, so to say, in parallel. And what I do when I do quantum jump Monte Carlo, for instance, I sample, so to say, this tree that I generate. Yeah, so I create samples of these paths a long time, and then decide at each junction whether I emit now a photon or whether I don't. But here I have all the branches of the tree, in the sense, still in parallel.
Yeah, that's interesting. That's nice. Yeah, so instead of keeping one wave function of the universe and keeping all of you've sort of traced out into subpiece. You've traced out onto different subspace if you want to, for each number of photons at each time. And okay, yeah, that's great. I think I
indeed. So because I just don't commit, I keep everything in parallel, but I can also commit. And I mean, this is how you generate, for instance, the trajectory that I'm showing here in this plot. Yeah.
Gotcha. Okay. Excellent.
So just maybe okay, saying this. So what I'm aiming at is now the development of this thermodynamic analogy, right? So this is what we are trying to accomplish now. And this is now having this conditioned state, which gives you this probability. Because I mean, this is, I think, a quantity which we can relate to. Yeah. So you observe a system for a certain time t. How likely is it to observe k photons? Well, the answer is just given by solving this set of coupled equations up to a certain time t, and then take the trace of these row k matrices. And then you can construct this diagram. It's computationally demanding, but okay, in theory, it's possible. So now, here comes a step, yeah, that is maybe it's the first leap of faith, yeah. So at long times, this function is actually following a so-called large deviation form, yeah, and details will follow, and not many details, but I so to say also tell you that this is not something completely crazy, but that this is something which is generic and actually a principle upon which we build thermodynamics, although nobody is really telling you about this. So the point is that we have here an extensive parameter, which is time. Yeah. And so in equilibrium statistical physics, the extensive parameter one typically looks at is the volume or the particle number. Yeah. And then you, I guess, don't question it there, that these probabilities are given by the exponential of this extensive quantity times some function. And this function actually is in general the so-called large deviation function, hence the name, large deviation form. But in fact, it's actually an entropy density. Yeah, so it's basically telling you how likely it is to have a certain, to have microstates that have actually k upspins in an ensemble containing n spins. Yeah, so this is how you would build thermodynamics. Formally, you would say, well, this is a consequence of this large deviation principle, which is basically a glorified central limit theorem. Okay, so now accepting this, and I admit, okay, this is something to take in if you haven't heard this before, then we can now continue and see what we can do with this. Yeah, so we have now a long time form of this probability distribution. So this is, just to say, valid in the long time limit. Now, what I want to do now, I want to introduce a counting field, and bear with me, so that makes or changes, so to say, the probability of certain trajectories. So you see this here at this level. Yeah. So let's say rho is the state, the conditioned state on observing k photons. And now with this prefactor here, which is this counting field, and I will again use an analogy later to explain what it does. You see with this prefactor here, you, depending on the value of S, whether it's positive or negative, you make this conditioned state, the appearance of this conditioned state in the sum, yeah, more likely or less likely. And by this you tweak, so to say, the probability with which you observe k photons in your trajectory. Yeah, if S is very large and positive, you see having trajectories that contain k photons, a large number of photons, is exponentially suppressed, so they won't occur in this ensemble. And this is, so to say, at the theoretical level, the idea, yeah, that underlies this making rare events typical story, because you can also do it the other way around. You can also amplify trajectories with a number of photons that are typically not abundant in your ensemble. Yeah, just to show you how this works. Yeah, I mean, you just look at this abstract formula, but you can also do a hands-on example. So we take a trajectory that has 3 photon emissions at certain times, yeah, here indicated by these blue strokes. And our microstate, expressed in terms of these spins, would look like this. Yeah, so we have 3 upspins. And the probability of this is pt of 3, yeah, because we have 3 upspins or 3 photons counted. So now what this construction is doing, it now assigns to each of these upspins a factor, which is e to the minus s. Yeah, and you have seen this before. Yeah, this is exactly what you would do if you had a spin system and you applied a magnetic field. If you wrote down the canonical state, then in your Boltzmann factor, you would, due to this magnetic field term, now introduce for each spin that upspin that is contained in a microstate, an e to the minus b factor, field strength factor. Here it's e to the minus s, so each upspin is penalized, well, or enhanced, depending on the sign of s, when you introduce this biasing. So, and what you can also do now is you can write an equation of motion for this biased state, which looks pretty much like the normal master equation. The only thing is that here in front of this quantum jump term, you get an e to the minus s. And you see already that there's a problem here. So because this is, if you now analyze this equation, it's actually not a proper quantum dynamics. Yeah, so you cannot straightforwardly implement it on a device. It will not run in nature naturally. So you have to do something, and we are going to talk about this later when we get to the point where we want to implement this on a quantum computer. But just from the formal side, this is an allowed operation, and this generates, so to say, biased ensembles where I reweight the probability of certain trajectories according to the number of photons they contain. So at the formal level, I can also do this. So I can now look at the long time limit of this state rho s. This is written like this. Yeah, so I just have the large deviation form. So this entropy density is popping up in it, the large deviation form of this rho k of t, which shows up here. And now you see already I can evaluate the sum in principle by using a saddle point approximation, which gives you actually the Legendre transform in the argument. And this allows us to introduce, as we do it in thermodynamics, a free energy. So in some sense, we go now from this formulation of our thermodynamics in terms of entropy density to a formulation to a, let's say, canonical-like ensemble, which has the free energy as the relevant quantity. So now it's time for an intermediate summary, but because I guess this, if you haven't heard this before, this is maybe a lot to take in. So I really want to go through what I just said very slowly again, because this is really important to understand, so to say, on the basic level in order to make sense of what is going to come next. So basic premise is that emission events of an open quantum system can be analyzed through a thermodynamic analogy where we identify quantum trajectories with microstates. And this formalism gives rise to this free energy density that I now can compute using the procedure that I laid out before. And I get something like a free energy density, which is some object which depends on discounting field or biasing field S that I introduced, which allows me to make certain trajectories more or less likely depending on how many photons they emit, how many photons they contain. And if this still looks weird, no problem. Let's just use it, and let's see what we can actually do with this quantity. So this quantity we can now use to calculate cumulants of our dynamical order parameter, which is the number of photons emitted per time. Yeah, I mean, ignore this middle bit and just accept what I write here on the right, because this expression here, you can reformulate that you get the expression of the right-hand side. And this is definitely something you have seen in a thermodynamics class, because this is, so to say, telling you that the order parameter that you are interested in analyzing in order to understand the equilibrium properties of your of a system at a thermodynamic equilibrium is actually given by the derivative of the free energy with respect to the conjugate field. Yeah, so if you were to deal with the magnetic system, you would have here the magnetization density, and this you obtain by taking the derivative of the free energy with respect to the magnetic field. So the structure is completely analogous to what we typically use when doing equilibrium statistical physics and using a thermodynamic description of many body systems. So, and in this sense, and this is also something I want to bring across now again, discounting field S, which looks a bit weird, yeah, is super analogous to actually a magnetic field, yeah, applied to the spin. So, for instance, you can think of the original ensemble of trajectories that is generated by your open system. Yeah, we'll just generate output. You have an ensemble of trajectories for which you can do counting statistics and so on. And now what you do is you go from this a priori trajectory ensemble, which is maybe the microcanonical ensemble, you can draw this analogy, to something which you would then perhaps identify as the canonical trajectory ensemble, in a way that you, so to say, assign an energy to each of the microstates, which is very simple because it's just, so to say, spins in a magnetic field. And this everybody of us physicists has done in their lives. Yeah, so going from a microcanonical ensemble to this kind of canonical ensemble. And this is, so to say, what the gist is of this thermodynamic analogy. So, if there are questions, now is the time, because now we change gears a little bit and we want to ask ourselves, how can we implement this on a quantum computer? And then later we ask the question, why would we even want to do this? Yeah. So you have to tell me whether I should stop or not. But if not, then I just keep going. All right. So
maybe just summarize quickly the kind of high level picture. So essentially, you know, we're looking here at the different. It's a thermodynamics of the types of, you know, emissions or trajectories you could get across an ensemble. You know, if you run this many times,
indeed,
not of the particular individual instances, but really the ensemble.
Yeah.
And you know, maybe two questions, and you'll probably get to this, but one is, you know, tell us a little more about the kind of new insight or different ways of looking at what we know that this tells us.
For the moment, it's just an observation. So we will put it to use now, but I'm just telling you that think of, let's say, a non-interacting spin system. Yeah, so all microstates appear with the same probability there. So what you do now, or what you can do in order to change this, you can introduce a magnetic field. And then you, according to the strength of the magnetic field, you make some trajectories or some microstates more likely and others less likely. And if you remember in the first part of the talk, I said one thing one could want to do is to make certain outputs of an open system more likely than compared to what their likelihood is in nature. For instance, you could think of a situation where we want to create a single photon every, so to say, in a regular space, in regularly spaced time intervals. So this is something that will never happen. But it can happen as a rare event. And now you can ask, what do I have to do in order to make this rare event typical? But okay, we will get to this. And this is not the easiest talk to give, but I promise you the build-up is sound, and we will get to a question that has also, let's say, broader relevance linking to this glass problem that I alluded to at the very beginning. So let's be patient, and I try to move forward also within the amount of time that still remains. So
maybe one quick question from the audience here from Deepak. Time is like temperature?
No. No. Time is like volume or particle number in this case. This is the extent, because we are looking at the time limit, in the long time limit. So everything is only this large deviation form is strictly valid in the t goes to infinity limit, but this is like thermodynamics. There we also look at the thermodynamic limit, large particle number, large volumes. Only then you can exploit these relationships and define entropy, density, and free energies and so on.
And maybe a quick question. Let's see if we know what Jorge is referring to. He says, can you understand parts of these phenomena in terms of KMS states or the KMS framework? Is this relevant here?
If you spell out for me what KMS means in this context.
Yeah, maybe Jorge spell it out. I'm also not quite sure which one you're referring to. Okay, let's move on. Thanks, Igor.
Okay, we can get back to this, but okay, I promise it will become increasingly more transparent. So, okay, so this is now the basic idea laid out. And now if we go to the quantum computer, so we have several issues to deal with. First, time is discrete. It's not continuous, because it's a gate-based evolution that we can implement on the quantum computer. So we have like a clock that advances forward in discrete steps. And ideally, the quantum computer runs a closed system dynamics. So we don't have an open system there, but we have to generate an open system by entangling the degrees of freedom of interest with some auxiliary degrees of freedom that we then trace over and thereby implement dissipation. So I will here, for this purpose of this talk, show you a basic proof of principle experiment conducted on this IBM Q Jakarta machine. And what we will do is we will generate biased trajectory ensemble, not in this, let's say, boring way that I did now, where I introduced effectively a magnetic field. I want to make it more interesting. I want to look, for instance, also at situations where I enhance trajectories which show certain correlations. This is, for instance, a situation shown here. So let's say this is my non-biased trajectory. But what I will do is I apply this reweighting factor with a counting field S here, and that each neighboring upspins acquire this factor e to the minus s. And if s is negative, I can dramatically enhance the probability of two upspins appearing next to each other. So like this, I induce correlations in my system. And now, of course, the question is, how can I make this work on an actual device that obeys quantum mechanics? Because before I showed you that this equation of motion that you get when introducing this counting field, this deformed master equation, is not a physical one. It doesn't for instance, preserve norm of the state. But we'll get to this. So first, discrete dynamics. Here, the name of the game is collision model. I guess probably the audience is familiar with this. So the idea is here that we have a system of interest. This is just a spin for the purpose of this demonstration. Then we have an ancillary qubit, and then we entangle this system of interest with the ancillary qubit via a unitary collision, so to say, just an application of a unitary operator. And then what we can do is we can measure now the ancillary qubit state after this collision. And then I can look at the system, and depending on the measurement result, the system state is either this K0 times the original state or K1 times the original state, where these Ks are so-called Krauss operators that you can construct from this collision unitary. So if you don't resolve the measurement output, you can still write an equation of motion. You can say, well, the state for before the collision is this pure state psi. You see it here. But then you now have either your ancilla in the state 0 in the measurement. You're not looking, but you know what the probability with which this is happening. This is exactly happening with this probability P0, which is given by this number here. Or you have your ancilla in the state 1, and this would correspond to this term here, to this operation on the state of your system, which occurs with probability P1. And you sum them up, and then you get a proper quantum evolution, which is not proceeding in continuous time, but in discrete time. And this goes under the name quantum map. Essentially, you have your initial state, you apply this quantum map, and then you get your state after the interaction between the system and the ancillary qubit. So this is how you implement open system dynamics on your quantum computer. And a concrete system could, for instance, which very much resembles this basic two-level system that I spoke about before, is this system here, where we have our system and we have ancilla and we have some coherent Rabi frequency-like drive between the two states of the system. And we have this collisional coupling, let's say, between the ancilla and the system, which leads to entanglement and, in effect, open system dynamics on the system qubit alone if I trace over the ancilla. So in some particular limit, which I don't want to dwell on, this actually gives you back this continuous time master equation if you properly scale these constants omega and kappa. So now, how do I get to the trajectories? Actually, here it's super nice because you can just look up the states of the ancillas on your quantum computer. So you have your system state, you collide with the first ancilla, with the second, with the third, with the fourth. And these are like the time bins that I mentioned. So this analogy between these photon emission events and the spin up and spin down microstates is actually much more manifest here on this discrete quantum computer, because now when measuring this ancilla, this ancilla, this ancilla, this ancilla, I just get a number 0 or 1, for each of the measurements. And such sequence of measurements, the measurement outcomes, just give us trajectories. So this is one possible one, another one, another one, and another one. So it's much more straightforward than what I talked about before to obtain these trajectories on a quantum computer. So in effect, if you don't like this picture, you can also translate this in our beloved circuit language. So now let's think of what we can do, what kind of observables with respect to which we can bias the trajectories we can come up with. So we have our quantum trajectory here. It's just 4 time units, 4 time units over which we propagate it, and then we have certain possibilities. And now you can look, for instance, of observables that are functions basically of these measurement results of the ancillas, functions of the trajectory, which just contains now a set of n numbers labeled by k1, k2, kn. So examples of interest are, for instance, linear functions. So I want to observe observe trajectory or observe functions that are so to say linear in these entries here. In the simplest case, this vector Pn is just the identity, so it's just the sum of counts. This is exactly the number of emissions that I showed you at the very beginning. But generally, you can also modulate, so to say, the weighting, and this would correspond in the spin analogy to a spatially inhomogeneous magnetic field, this Pn. But you can also do more. You can also look at nonlinear functions, the correlations. You can, as I showed you a couple of slides back, ask, okay, what's the probability to have two emission events next to each other? And you can make this arbitrarily complicated. So the point I want to make is that observables on these trajectories can be linear or nonlinear functions. And you can calculate the probability of such observables. And now you can ask, well, is there a way to modulate this probability? And for instance, you can think of asking a question, well, how likely is it to see emission after the first, the second, or the third, or the fourth time step? So this is really some data produced, which corresponds to the original dynamics, that is running on this collision model, and you see that you get a distribution that looks like something. And then you can ask yourself, now, can I actually change this original distribution in a way that maybe looks like here, so that it's very likely that I get an emission at time step 1, time step 2, time step 3, and time step 4. So this is the basic idea. So it's of course a very toyish model here because there are very few degrees of freedom. But you see what I want to do. I have an original probability, and I want to create a probability that suits my needs. And of course, more elaborate settings, this could be highly correlated trajectories, highly with interesting properties. So I want to make this relatively short because I also don't want to overload you with math, and I promise there will be some nice pictures following. But what you can do is now you can basically go through the same formalism as before, but not in continuous time, but in discrete time, and basically translate it from the master equation to the quantum maps. So long story short, what you find is that once you, for instance, want to generate a biased trajectory ensemble that makes the observation of certain values of such a linear observable more or less likely, what you have to do is to deform your map. And you find that unlike in what I showed you before, where we have k0 rho, k0 dagger plus k1 rho, k1 dagger, we have to introduce here this biasing factor. And this is exactly this, well, not exactly the same, but it's, so to say, of the same origin as the biasing factor that we also encountered in this deformed master equation that generates this deformed trajectory ensemble in discrete time. So what this map does, like all the examples that I showed you before, is the following. So we have, for instance, here 2 different trajectories, one where you have at time 2 an emission event and one at time 4. Then you see running, so to say, this evolution or this dynamics on your system enhances the likelihood of these trajectories. So this first trajectory will acquire this factor, and the second trajectory where I have 4 emission events will acquire this factor. And you can now imagine that when I make S large and negative, this trajectory here with the 4 emission events will be exponentially more likely than this trajectory with only 2 emission events. And this is the basic idea, that allows you to enhance the probability of certain trajectories in your ensemble. But as I said before, the problem is that the evolution is completely artificial. I mean, we just made it up. It's a mathematical construct that does what we want, but has the issue that it's not physical. And at the level of these quantum maps, this can be seen immediately if you calculate, for instance, the action of the adjoint map on the identity. So which ought to be 1 for a physical dynamics, but it's not 1 because there's this nasty exponential factor here, which prevents this from being 1 in the end. And now the question is, what do we do? How can we construct a dynamics that is physical, meaning that can be run on a quantum computer, so that these bias ensembles are generated? And it all can be done via a technique that is called the Duke transform. And I have this grayed out here on purpose because I really don't want to discuss about this, because this is, again, complicated. This is linear algebra stuff. You're more than welcome to read it up in this publication here. The point is, it can be done. And what we have to do is we have to modify the ancilla qubit interaction in a particular way, for which we have also a constructive procedure. And just to show that this works, I show you this plot here, where we have a system, a qubit, evolving over 3 time steps. And then you see, when you evolve a system over 3 time steps, you can, so to say, have 8 possible trajectories, no photon emission up to 3 photon emissions. And now you see here basically 3 curves, a black one, black shaded one, a blue shaded one, and this red shaded one. And these curves are the curves that you get for certain values of this biasing field. The physical dynamics produces you the black curve. Yeah? And the solid line is, so to say, the numerical simulation of this process, and the circles are the results taken from this IBM Q Jakarta device. So the point is now that you want to go away from this physical dynamics. You want to generate this biased ensemble, which in theory can do. But I show you that this can also be done in practice. For instance, here we generated for s equals 2 trajectories where it's very unlikely to have a photon emission. So the weight is on this trajectory here. And you see, this matches very well with a prediction, and this result has been obtained on a physical device, on this chip of this IBM Q Jakarta machine. Likewise, you can also put s equal to -2, and you generate a deformed probability distribution where you enhance the probability of this 1, 1, 1 and the 0, 1, 1 trajectory. So bottom line is, it works. It can be done. And now you should ask, why should one care? Yeah, so with a really long build-up of this point 4 that I want to make now, because this is actually a super cool tool now to investigate interesting collective many-body dynamics that is difficult to simulate on classical devices. And in order to make the case, I want to make a very, very brief detour through the story of classical glass formers. And if you're interested in this, I can direct you to those papers here. So what is the idea? And it's, I think, best illustrated by showing you this kind of movie. It's just 4 snapshots taken at different times. And what this shows are simulation results of a supercooled mixture of a substance, or of a liquid, so to say, that contains 2 classical particle species. And what I'm plotting here is color code. It's not a density, it's what one call activity. So it's actually the amount by which particles are displaced in the course of time. And what you see in these trajectories is very nicely that you have these domains. Yeah, so you have here parts where the system is active, and you have parts where the system is inactive, in the sense that not a lot of motion is taking place. And what you see, I mean, if you again think about some kind of magnetic system in 2D, is a phenomenon that one would call coexistence. Yeah, so if here at longer times it's even more manifest. You see here space-time regions where nothing moves, a spatial region where nothing moves over a long time, and you see spatial regions where a lot of movement is taking place. And if you now plot, so to say, this activity, this displacement, which is an order parameter for this phase transition, as a function of the counting field that I introduced before, so you make trajectories with lot of movement more probable or less probable, depending on the value of the counting field, then you find that actually these glass-forming substances sit directly at the coexistence point of a dynamically active and a dynamically inactive phase. And if you now are able to change the counting field to a negative value, then everything will become active. And if you move it to the right, you will find trajectories where everything is inactive. So this counting field is a nice means to, like in a magnetic field, or like any external field, to move in between phases. And for these glasses, it's particularly interesting because they are thought to be sitting directly at this like first order phase transition point where you have coexistence between an active and an inactive phase. So yeah, we still have 2 minutes, I guess. So now what you can do is you can also try to build this analogy for a quantum system that is open. Yeah, and now we basically generalize the story that I told you for a single qubit to more qubits. And what I just want to put forward is a basic system that is also, I mean, if you have recently listened to talks about Rydberg quantum computing, this Hamiltonian will look strangely familiar. So you have here a term that effectuates coherent state changes, spin flips, and you have here interactions between spins, which takes place when when two spins are simultaneously in the excited state. So these Rydberg quantum simulators or quantum computers that would correspond to two atoms being simultaneously excited to the Rydberg state. And now you take this coherent dynamics and you couple it to ancillas, which, so to say, make your system open. And you do it in a way, what you do then is you basically observe your ancilla ensemble in order to get trajectories. But now you have also a second dimension. Yeah, before I showed you only time, now you have also space. Yeah, this is important. And what's also important is that you can show, I mean, this is just an easy proof, that the stationary state, so the long time state of the system, is actually completely trivial. If you look at this long time state, you will find it's proportional to the identity. So it's basically an infinite temperature state, which is completely structureless. And this is also kind of thinking that is being propagated in the context of glasses. These are also substances which approach eventually, after extremely long times, a thermal equilibrium state, which is boring. But the relaxation towards it is highly correlated, so that in practice you will never reach the state. So these are substances that will always live in the transient. And a consequence of this is this dynamical heterogeneity that I showed you before for these classical simulations. The problem is now for these quantum problems, you can only do simulations for much smaller sizes on a classical computer. Well, it's to be seen what the quantum computer can do later. But you see also manifestations of this already. Yeah? You see, for instance, here a system of 6 spins. And what I show here in the top panel is the system state. As a function of time, I look at now what is the probability for each of these 6 qubits to be in the excited state. And what you then see is, and you see the have here a region, a space-time region, which is, one would say, very active because changes of the local spins are abundant, which then moves on to into a region where, well, I have a huge domain which is slow, where changes of the spin states do not take place, coexisting, so to say, with a domain, and it's a big word, coexistence here in the system of 6 spins, coexisting with a domain where you have lots of movement. And you see this even more nicely in this signal of the ancillas. You see really that here you have a fast and active region, and here is a slow inactive region. And this is also a manifestation of this dynamic heterogeneity on these quantum systems, which you can only compute for very small sizes. So now you can say, well, this is completely crazy to now identify this as dynamic heterogeneity. And this slide is just to show you that this is not completely crazy, because although this system that I showed here is, so to say, not efficiently solvable on a computer, on a classical computer, you can now go to a limit which one would refer to as strongly dissipative. Yeah, so if dissipation is so strong that effectively this evolution of your many-body system is governed by classical equations of motion. And there you can solve now the dynamics for large system sizes. And I just invite you to look at this color plot. Don't look at this fancy 3D structure. So it's just this color plot. And there are things you recognize. There's, for instance, this counting field S in this direction. So S equals 0 corresponds to the physical point. This is where one is sitting if one doesn't do the biasing. And in this direction here, I increase the interaction. So now, without interaction, I get this type of space-time plot. So where blue corresponds to spin up and white corresponds to spin down. And I see it's just noise. So it's a non-interacting problem, which doesn't show anything interesting. But now if I crank up the interactions, you see this here, then suddenly moving along this line, a ridge appears. So, and you see now, when I change my counting field to slightly negative values, I go to this active phase. If I change it to slightly positive values, I go to this inactive phase. And I'm walking on this ridge, and what this means thermodynamically, again, I'm sitting on the coexistence point between two dynamical phases. And you see this very nicely in this trajectory here, where you have these space-time bubbles, either corresponding to the inactive phase or to the active phase. And this is really dynamical heterogeneity at its best. That is also predicted for these classical glass forming systems. Oh, sorry, I should have displayed this. So wrapping up, you can, of course, now do this also for the small system. This analysis of this so-called dynamical phase diagram. And you can plot here as a function. You can plot here on the x-axis the counting field, like in the previous plot, and you can plot here the interaction strength. And then you see sufficiently strong interaction, something's happening. Yeah? And for instance, this trajectory that I showed you before was taken at this point here, yeah? Where you see, indeed, if you now look at the phase portrait of this, of the dynamical phase diagram of this system, you see indeed that here in this region, you would expect to have a coexistence between a dynamically, in this case, uncorrelated phase and a correlated phase. Okay, this brings me to the last slide. Sorry, it's a bit busy, but what I want to say is, I hope I could convey an idea here about this, is that the output of an open quantum system can be characterized using a thermodynamic analogy, and that this allows to enhance and reduce the probability of certain trajectories emerging. And so to say, this is done by introducing a conjugate field, biasing field, counting field. This works in continuous time, works in discrete time. But long story short, it allows you to control, so to say, the statistics of the trajectory ensemble that is generated by your open system. So this is the story I want to say. And then I just take this work here, which I take the liberty to promote as a recent publication that we put on the archive on using machine learning to actually learn quantum channels on NISQ devices, also using an IBM Q machine actually to show that this works in practice. Thank you very much for your patience.
Thank you, Igor. And folks, this is a great time to repost your questions that we didn't have a chance to get to earlier. Maybe I'll just kick it off with a big question, big picture question on the first part. You know, you kind of showed us the counting statistics for, and now I realize that in a sense my question doesn't make a lot of sense, but let me ask it anyway, which is that you showed us, you know, these counting dynamics introduced from the point of view of these point-like unravelings or count processes. You know, one can also think of systems where the natural unraveling is the diffusive or heterodyne, homodyne.
Indeed, yeah. Signal. But can also I mean, here the biasing is done with respect to the counting, right? So they can do it also for different unravelings. So I can also do it for homodyne detection, for instance. This would give rise then to a different deformed master equation where you, so to say, bias against the photocurrent, where you make certain currents more likely than others. This is also possible.
I see. And in that case, do you end up with sort of an infinite continuous parametrized list of differential equations? Because here you have this discrete variable k, which is how many?
Yeah. Okay.
Continuous.
So, all right. So this I did. I mean, in the end, this hierarchy, you don't even need it, right? Because I only wrote this down because I always, I don't know. I mean, it's my personal bias. I understand it when looking at this hierarchy of equations, what happens actually. But at the end of the day, you see, you're only looking at this row of S object, which is kind of the Laplace transform of this row of K. And this again is just one equation for this object. So there's no longer a hierarchy of these equations anymore. So it's gone, this hierarchy, by looking at this Laplace transformed object. So the same you can do for the same, something analogous you can do for the homodyne detection, and then you get a master equation that also is not a hierarchy of coupled equations anymore, but just one equation that depends on this counting field in a particular way.
Excellent. I think there was a question here from Deepak, and it's a little bit earlier, so Deepak, feel free to chime in on kind of where it was. But the question was about what is the interaction Hamiltonian for the spin-spin interaction? I think this was somewhere towards the second third of your presentation. So let's see if we can get that.
So, okay, so interactions turned up twice. So, I mean, here, this is a part where it shows up just to make the system interesting and to introduce some correlations because clearly here it costs energy to have spins next to each other. And this is probably also now a pedagogical problem of my talk at all, because, okay, I'm using spins here for real particles living in space, and I was using spins here, yeah, when to represent this trajectory. But you see, these operators now act on trajectory space. I have to work on this, yeah, but it's hard to compress all this information into one single talk. So I should probably give a few more lectures about this. But here it's, so to say, interaction that is introduced at the level of the biasing, which allow us to enhance or decrease the probability of certain trajectories. And you see it acts on consecutive spins, so it makes the appearance of such consecutive upspins more or less likely.
Excellent. Maybe a question from Shashi. Is there a, towards the end of your talk now, do you observe that this looks a lot like, actually before that, let's go back to an earlier question about KMS from Jorge. He said, very nice talk, extremely nice. Immense states that satisfy the Kubo-Martin-Schwinger condition in operator algebras. These are used a lot in work that relates to quantum statistical mechanics. So I think it's doing this kind of QFT type of connection.
Yeah.
Feel free to comment.
I cannot comment because I really have not even semi-knowledge of this, if I'm honest. So I better say nothing.
Okay, that's perfectly fine.
Not to embarrass myself, yeah. So
it's all right. Well, you're pulling a lot of different domains together. And can you tell us a little bit more on, we saw some very nice experiments on a few of these qubits and IBM devices and others. What are the main limitations? How scalable are these? If you want to do this now, open system quantum dynamics on 50 qubits, 100 qubits, what is the, could you have done that, or is there, what's the bottleneck to scaling it?
Okay, so the claim is that this can be done because at least these operations that you need to do in order to introduce or implement this bias dynamics, this loop transform on your device, you can construct, let's say, constructively. I mean, this is not a complicated problem you have to solve in order to identify these operators. So how this all scales, I don't know, to be honest. So how efficiently this can be done in the end. But so to say, what limited us already in the present experiments is, of course, the coherence time. So we could only have a few collisions before things, started to deviate, and obviously decoherence kicked in. We would have loved to go to longer trajectories, but I think I don't quite recall what the reason was. I think it was also limitation of the architecture that we could only do 3 and got reliable results. But of course, one could try with a different chip and see how far this takes us. But long story short, I think the bar is not so high, if I'm honest. Because these are 6 system qubits. They come with 6 ancilla qubits, so that's 12. And let's be optimistic. On a computer, you can maybe do 30 qubits on a classical computer. So this would limit, because you have always take this by 2. This would give us 15 system qubits. So I would think that a quantum computer relatively quickly would outpace, so to say, a classical machine here, even if it's not perfect. Because the scaling for the classical machine is definitely not favorable here. Even less so if you want to have longer trajectories where you assign, so to say, to each of these time slices a slice of ancilla. So you can imagine now, every time step, this system chain has to collide with a chain of ancillas in another one, and another one, and another one. So you run out of qubits on your classical computer very quickly.
All right. Well, Igor, I think this brings us to see if you want to leave us with any final thoughts here.
Well, thank you very much for having me. It was a great pleasure, and I hope I could get you interested in this nice interdisciplinary aspect of quantum computing, statistical physics, and in the end, non-equilibrium statistical mechanics. Thank you very much.
Thank you, Igor. And folks, this talk will stay recorded, so you can go back and rewatch it. But to know what's coming up, click like and subscribe, and we will see you next Friday at noon Eastern Time. Have a great day.